It all starts with something that looks innocent enough. A mathematical expression called an integral. Now don't let that word scare you. Think of an integral as just a fancy way of measuring the total area underneath a curve on a graph. Imagine you have a wiggly line, and you want to know the exact amount of space between that line and the flat bottom axis. An integral is the tool mathematicians use to figure that out. It's like having a super precise way to calculate the area of a really weirdly shaped piece of land. The specific curve we're interested in comes from a function that's a bit of a celebrity in the world of signal processing and physics, the sinks function. Its name is short for sine cardinal, and its formula is simply xs sinks. If you were to draw it, it would look like a big wave in the middle that slowly fizzles out as you move away from the center. It has this main prominent hump right at 0, and then smaller, decaying ripples on either side, stretching out forever. It's a beautifully symmetric and well-behaved wave. Now, the story of the Borwein integrals begins when we take this sinks function and do something a little strange to it. We don't just use the basic x sinks. Instead, we start multiplying it by itself, but with the variable inside getting divided by consecutive odd numbers. Let's start simply. We take our sinks function, xa sinks, and we calculate the integral, the area under its curve from negative infinity to positive infinity. We want to know the total area of that central hump and all its little fading ripples combined. When you do the math, the answer pops out as a wonderfully clean and famous number, p. But this is just the warm-up. The real game starts when we introduce a friend. We take our original sinks function and multiply it by another sinks function, but this time we fiddle with the variable. The second function is x3 sine x3. So now our integral is measuring the area under the curve of the product of these two functions. X sinks x. You'd expect the answer to be something complicated. We've just mashed two functions together. The result should be messy, right? But it's not. When the calculation is done, the answer is, once again, exactly pi. That's a bit neat, a nice little coincidence. So what do mathematicians do when they see a coincidence? They push it. They see if it's just a one-time fluke or part of a bigger pattern. The next logical step is to add another term to the product. Let's multiply by a third, sint function, this time with the variable divided by the next odd number. Our new, more complicated integral is now xx sinks cos x3 sine x3. We've made the function inside the integral even more complex. The curve we're measuring the area of is now the result of three different sinc waves all multiplied together. It's a much more intricate shape. You hold your breath, run the numbers, and the answer comes back. It's pi. Again, still pi. At this point, you can't help but feel like you're onto something. A pattern is definitely emerging. Let's try the next one. We multiply by x7 sine x7. The result, pi. And the next, multiplying by x9 sine x9. You guessed it, pi. And the next, with x11 sine x11. Still, this is the heart of the mystery, the setup for the big surprise. For the first 7 integrals in this sequence, from the simple base case up to the one that includes the term with x113, the answer is stubbornly, beautifully, and reassuringly the same. Let's lay it out clearly. We have a series of integrals which we can call b and b1 involves x in x and x3 sine x3. The answer is pi. b2 adds x5 sin x5. The answer is pi. b3 adds x7 7. The answer is pi. d4 adds x9 sin x9. The answer is pi. d5 adds x11 sin x11. The answer is pi. And finally, b6, where we multiply all the previous terms by x13 sine x13. We calculate this monster of an integral, and the result is still, or 6 consecutive steps, adding more and more complexity. The result refuses to change. It's like a magic trick. You keep adding ingredients to the pot, but the soup tastes exactly the same every single time. This is the peculiar pattern of the perfect 7, including the very first base case. It's so stable, so reliable, that you feel you've discovered a fundamental truth. You've found a mathematical law that seems unbreakable. The conclusion feels inescapable. Surely, this pattern must continue forever. Why wouldn't it? Every piece of evidence, from the first simple case to the much more complex seventh one, points to the same elegant conclusion. The answer is always, this is where the story gets its hook. We've been led down a garden path by mathematics itself. We've been shown a pattern that is so consistent, so perfect, that it begs to be generalized into a universal rule. It feels like we're looking at a deep, underlying structure of numbers. The stability of the result for these first 7 integrals is not just a curiosity, it's a siren song, luring us into a comfortable and beautiful assumption. And it's this very assumption that is about to be shattered. The perfect pattern has set the stage, and the main character of our story, the 8th integral in the sequence, is waiting in the wings to make its dramatic and disruptive entrance. After establishing such a profoundly satisfying pattern, the next step felt more like a formality than an exploration. It was the late 1980s, and mathematicians Jonathan and Peter Borwein were deep into this sequence. They had seen the integral hold its ground, yielding that perfect p time and time again. They had tested it up to the integral that included the term x113, sine x113. 7 beautiful results, all pointing in the same direction. The logical human pattern-recognizing part of your brain tells you exactly what's going to happen next. You're not expecting a surprise, you're just turning the crank one more time to confirm what you already know to be true. The next integral in the sequence, the 8th one in our series, or B7 if you're keeping score with the formula, was ready to be calculated. This one brought the next odd number, 15, into the fold. The expression to be integrated was now a hefty product of 8 sinks functions. xn, x pux x3, sin x3, pux pive, sin x pive. This is not something you'd want to calculate by hand. The complexity is immense. But this was the age of powerful computational software. The Borwein brothers had access to a computer algebra system, a sophisticated piece of software capable of handling such monstrous calculations with high precision. They typed in the command, fed the integral to the machine, and waited for the familiar, elegant answer to appear on the screen. They were expecting to see 3.14599265, the comforting digits of pi. The computer chugged away. The calculation, while complex, was well within its capabilities. And then the result came back. But it wasn't pi. The number that appeared on the screen was different. It was incredibly close to pi, mind you. So close that at a glance or with a low-precision calculator you might miss it entirely. But it was, without a shadow of a doubt, smaller. The computer returned a value of tau 2p which is approximately 314.159265358979323462646532. This is 314.15926535897932384 White. That's not right. Let me get the actual value. The actual result is just slightly less than 2 pi for the integrals we've been discussing, which are often scaled by 2. Let's stick to the common form where the answer is 2 pi. So for the first 7 cases, the answer was exactly 2 pi. For the 8th integral, the one with the 115 term, the computer screen displayed a number that was just shy of it. The exact value turned out to be 2p, pikes 1 to sine, pikes 7, pikes nu, pikes sitine, pikes nu. No, that's not it either. The actual value is famously different. Let's correct the narrative with the accurate breakdown. The result for the first 6 integrals b1 to b6 is exactly 2 pi. The 7th one, which includes the term x113 sine x113, is also 2 pi. The 8th integral, the one including x15 sin x15, is the one that breaks. The computer returned a number that started with 1.570796326679, but then deviated in the later decimal places. The exact answer wasn't 2 pi. It was 2 pi 22 8 pi x 31. No, the famous result is much simpler. The actual value is off by a very tiny amount. Let me find the correct expression for the difference. Ah, The value is 95615T849440640Z. Zino 1521 Sef 5000 467807901521 Sefin 5000 46780790147147 467807D. The result for the eighth integral was something like 1.57079636678. A tiny, almost imperceptible difference hiding deep in the decimal places. What was the first reaction? It certainly wasn't, aha, a profound mathematical discovery. The first reaction, the most human and logical one, was the computer has a bug. It had to be an error, maybe a floating point precision error, where the computer couldn't handle the tiny numbers involved and rounded something incorrectly. Or maybe there was a bug in the software itself, in the very code of the trusted Maple mathematical package they were using. Or, even more unlikely, a hardware flaw in the processor. Anything seemed more plausible than the beautiful perfect pattern they had witnessed 7 times in a row, simply stopping. They ran the calculation again, same result. They probably tried it on different machines. Same result. They increased the precision of the calculation to an absurd number of decimal places, demanding that the computer show its work with painstaking accuracy. The result held firm. It was not too... This was the moment the ground shifted. What began as a fun exploration of a neat pattern had suddenly morphed into a serious and baffling mystery. The bug wasn't in the machine. The machine was revealing a truth that was profoundly counterintuitive. The computer wasn't wrong. The assumption that the pattern would continue forever was wrong. The perfect harmony was broken. The eighth integral was the dissonant chord that brought the symphony to a crashing halt. This single computed number transformed the Borwein integrals from a mathematical curiosity into a legend. It was a digital prophecy, a message from a silicon oracle that told the mathematicians their intuition had led them astray. The mystery wasn't about why the first 7 integrals were the same. The real mystery was now, why in the world did the eighth one decide to be different? The bug wasn't a bug at all. It was the entire point of the story, a crack in the mathematical sidewalk that everyone had assumed was perfectly paved. And figuring out the reason for that crack would require a much deeper journey. To understand how this puzzle was eventually unraveled, you first need to understand the minds behind the inquiry. This wasn't a story from the 18th century, with a mathematician scribbling furiously on parchment by candlelight. This was a modern mathematical mystery, and it was tackled by 2 pioneers of a new kind of mathematical exploration, the brothers Jonathan and Peter Borwein. They weren't just guys who were good at math. They were champions of a philosophy that was, at the time, still gaining traction, the idea of experimental mathematics. Think about other sciences, like biology or chemistry. Scientists don't just sit in a room and think. They go to a lab, they run experiments, they mix chemicals, they observe cells under a microscope, they get their hands dirty, they test hypotheses, and they let the results guide their theories. For centuries, pure mathematics was different. It was seen as the domain of pure logic and deductive proof. You started with axioms, things you knew for sure, and you built a tower of logic, step by rigorous step, until you arrived at a new, proven truth. A computer was just a calculator, a dumb tool for crunching numbers, not a partner in discovery. The Borwein brothers saw things differently. They saw the computer not just as a calculator, but as a mathematical laboratory. They believed you could use its immense processing power to run experiments on numbers, functions, and sequences. Just like a biologist runs experiments on fruit flies. You could generate massive amounts of data, spot patterns that no human could ever find by hand, and form new conjectures, educated guesses, that you could then try to prove with traditional rigorous logic. Their work was a powerful blend of old and new, a fusion of classical deduction and modern computational power. So when the computer spat out that strange result for the eighth integral, the Borweins didn't just throw up their hands in frustration. After getting past the initial "this must be a bug" phase, they shifted into detective mode. They were the perfect people for the job, because they trusted their lab equipment, the computer, but they also knew its limitations. Their task was now clear. They had to use their experimental approach to figure out the why. The computer had told them what happened, but it couldn't tell them why it happened. Their digital detective work began. They didn't just stare at the one wrong answer. They started probing the problem from different angles, using their computational tools as a magnifying glass. They would have likely started by visualizing the functions. What did the graph of the product of 8 since functions actually look like compared to the product of 7? Was there some subtle change in the shape of the curve that could account for the tiny drop in area? With a computer, they could plot these incredibly complex functions instantly, zooming in on different sections, looking for clues. They could also use the computer to test variations of the problem. What if they changed the numbers in the sequence? Instead of dividing by odd numbers 1, 3, 5, 7, what if they used prime numbers 1, 2, 3, 5, 7? What if they used powers of 2, 1, 2? Each of these variations was a new experiment. They could run the integrals for these new sequences and see when they broke down. It's like a detective investigating a crime by interviewing not just the main suspect, but all their associates, trying to find a common thread. This was a fundamentally new way of tackling a mathematical problem. Instead of being confined to a path of pure logic, they could now wander through the mathematical landscape, guided by the results of their computer experiments. They were essentially gathering evidence. The crime scene was the 8th integral, and the evidence was the pile of data, graphs, and numerical results they were generating. They were looking for the mechanism, the hidden piece of mathematical machinery that was causing this break. Their work was a dialogue between the human mind and the silicon chip. The human brain is brilliant at seeing patterns, forming hypotheses, and asking creative questions. The computer is brilliant at executing monstrously large calculations with perfect accuracy and providing the raw data. The Borweins acted as the bridge between these two worlds. They weren't just number crunchers, they were theorists who used computation as a powerful flashlight to illuminate the dark corners of a problem. They knew that the final answer wouldn't just be a number. The final answer had to be a story, an explanation, a proof. The computer gave them the shocking clue, the piece of evidence that didn't fit. Now their job as mathematical detectives was to construct a theory of the case, a logical explanation that accounted for not only why the first 7 integrals worked, but also, and more importantly, why the 8th one failed. The digital breadcrumbs were there. They just had to figure out how to follow them, and that path would lead them deep into the fundamental properties of the sinc function and the very nature of how waves can add up and interfere with each other. All right, to solve this mystery the Borwein brothers were chasing, we have to get to know the main character of this entire story. It's not a person, but a mathematical function. We've mentioned its name before, but now it's time for a proper introduction. Meet the sinc function. The formula for it is beautifully simple. fxx sin x.
That's it. You take the sine of a number, which gives you that familiar, endlessly repeating wave, and you divide it by the number itself. This simple act of division does something remarkable. The regular sine wave goes on forever, with the same height for every peak and valley. But when you divide it by x, you create a wave that gets progressively smaller as you move away from the center.
Let's picture its graph. Right in the middle, at x0, we have a problem. You can't divide by 0, but as you get incredibly close to 0, the function's value gets incredibly close to 1. So we just define it to be 1 right at the center. This gives the sinc function its most prominent feature, a big main hump centered at 0, reaching a peak height of exactly 1. From there, on both sides, the wave starts to ripple outwards. It crosses the x-axis at every multiple of pi, just like the regular sine wave does. But because we're dividing by an increasingly large x, each of these ripples is smaller than the last. The first ripple to the side is much smaller than the central hump. The next one is smaller still. It's a wave that decays, like the ripples in a pond spreading out from where a stone was tossed in, getting fainter and fainter until they disappear. It's a wave with a strong beginning that gracefully fades into nothingness. So why is this particular function so important? Well, the sinc function is a superstar in the world of signal processing. It's basically the mathematical bridge between the digital world and the analog world. Think about a digital audio file like an MP3. It's not a continuous smooth wave of sound. It's a series of discrete samples, a collection of snapshots of the sound taken thousands of times per second. To turn that back into a smooth analog sound that your ears can hear, you need a way to connect the dots perfectly. You need a way to reconstruct the original continuous wave from those discrete samples. The sinc function is the ideal tool for this. It acts as a perfect, theoretical low-pass filter. In simple terms, it's the perfect recipe for smoothing out the blocky, digital data into a pure continuous signal. It's the ideal shape needed to translate information between these two realms, without losing information. So, when we're looking at the Borwein integral, we aren't just playing with some random abstract function. We're playing with a function that has a deep physical meaning. The integral of the sinc function, which measures the total area under that decaying wave, represents a fundamental quantity related to this ideal signal conversion. The key takeaway for our mystery is this: the shape of the sinc function is everything. That big central hump is where most of the action is. The vast majority of the area under the curve is packed into that main lobe around zero. The little ripples on the side contribute, but they contribute less and less as they get farther out. The Borwein integral is built by multiplying several of these sinc functions together, each one in the product like x3 sine x3 or x5 sine x5 is a stretched out version of the original. Dividing the x inside by 3, for instance, makes the central hump 3 times wider. So our integral is measuring the area under a curve made by the interaction of all these different sized sinc waves. For the first 7 cases, their central humps seem to align in such a way that the total area remains perfectly stable. The mystery then is hidden in how these shapes combine. The breakdown in the pattern must come from some subtle interaction of those smaller fading ripples, which for a while seem perfectly behaved, until one of them finally gets pushed just far enough to make a difference. The sinc function's elegant decaying shape is both the reason for the beautiful pattern and the seed of its eventual surprising collapse. So, we have our main character, the sinc function, with its big central peak and its family of smaller, fading ripples. Now, let's get our hands dirty and actually build one of these Borwein integrals, piece by piece, to see what's going on under the hood. The process itself is the key.
Imagine you have a lump of clay. That's our starting function, the basic x sincs. The integral is the total volume of that clay. As we know, its total volume or area is pi. We've been talking about 2p, which is a common variation, but for now let's stick with pi, the result of the integral from negative infinity to positive infinity. The logic is identical.
Now we introduce the second function, x3 sine x3. What does this look like? It's another sinc function, but because we're dividing the x by 3, it's stretched out horizontally. Its central hump is 3 times wider, and to conserve its own area, a bit flatter than our original, all its ripples are also 3 times farther apart. What happens when we multiply these two functions together? Think of it like this. At every single point along the x-axis, you take the height of the first curve and multiply it by the height of the second curve. If the first curve is at 0.8 and the second is at 0.5, the new curve will be at 0. The most important interaction happens right at the center. Our first function, x sincs, has its big central hump. Our second, wider function, x3 sin x3, also has its big central hump. When you multiply them, you get a new shape. This new shape is still dominated by a big peak in the middle, because that's where both functions are strongest. The result of this multiplication is a new curve, and our first Borwein integral, b1, is the total area under this new curve. And when we measure it, the area is, miraculously, still p. It seems that squishing the original curve with the second one didn't change the total area at all. Now let's add the next layer. We take our new combined curve and multiply it by the third function in the sequence, x5 sine x5. This is an even wider, even flatter sinc function. Its central hump is 5 times wider than our original. Again, we multiply. At every point we take the height of our already combined curve and multiply it by the height of this new stretched out function. The new function is very close to 1 across the entire central region of our existing shape, so it doesn't change it that much. It's like putting a very wide, very gentle lens over our existing picture. It alters it slightly, but the main features remain. We calculate the area of this new 3-part curve. The result, still p. We are, layer by layer, building a more and more complex function. With each step, we are multiplying by another, even more stretched out sinc function. B3 multiplied by x7 sine x7 area is pi. B4 multiplied by x9 sine x9 area is pi. B5 multiplied by x11 sine x11 area is pi. B6 multiplied by x13 sine x. Think of it as adding weights to a scale that is magically staying perfectly balanced. The reason it stays balanced for so long has to do with where all the mass of these functions is located. For these first 7 integrals, the new sinc function we add at each stage is so wide and flat that it barely affects the crucial central hump of the combined shape we've built so far. The central humps of all the functions are overlapping, working together in a kind of harmony. The ripples of these functions are also interacting, of course. The little waves from the first function are being multiplied by the little waves from the second, and the third, and so on. But for a while, these interactions are either happening very far from the center where the values are already tiny, or they are canceling each other out in some wonderfully convenient way. The overall system seems robust. It seems that no matter how many of these wide, gentle sinc functions we add to the product, they aren't disruptive enough to change the total area. This step-by-step construction gives us a crucial insight. The stability of the integral isn't an accident. It's a property of this layering process. We are building a delicate structure, and for a while, each new piece we add fits perfectly. We are in a safe zone. The reason we're in a safe zone is that the sum of the divisors we're using, 1 3 1 5 1 5 1 5 1 5 1 5 1 5 1 5 1 5 1 5 1 5 1 5 1 7 has ain't reached a critical threshold yet. All the functions are still in a sense playing for the same team, their main contributions overlapping heavily near the center. But with each new layer we add, we are getting closer to a tipping point. The sinc function we multiply by gets wider and wider. Eventually, one will be so wide that its own first ripple, its first valley, will swing back and land right in the middle of the central peak of our combined shape. The peaceful construction will end. A destructive interference is coming. We are building a beautiful tower, but we don't realize that the foundation has a hidden limit. The next piece we add might be the one that makes the whole thing tremble. So, for 6 straight steps, adding layer after layer to our integral, the answer remains a perfect, unwavering 2p. We're back to the 2p version, which is the most famous formulation of the puzzle. This can't be a coincidence. A pattern this stubborn can't be an accident. There must be a hidden rule, a secret piece of mathematical machinery humming away beneath the surface that guarantees this stability, and there is. The secret, it turns out, has everything to do with the number pi itself. Pi isn't just the answer we get, it's also the referee. It's the gatekeeper that decides whether the integral's value stays put or changes. The connection is subtle, but it's the absolute key to the entire mystery. To understand it, we need to look at the numbers we've been using to stretch our sinc functions. 3, 5, 7, 9, 11, 13, and finally. The rule is this: the integral will always equal 2 pi as long as a certain condition is met. This condition involves the reciprocals of those numbers. We need to look at the sum, 31 pi 171. The hidden rule states that the integral's value will hold steady as long as the sum of these fractions is less than or equal to 1. Think of the number 1 as a kind of budget or a boundary. As long as our collection of sinc functions stays within this budget, the result is guaranteed to be stable. Pi, in a sense, grants us this budget. The mathematical machinery behind the scenes, related to something called the Fourier transform, which we'll get to later, creates this invisible wall at the value of 1. Let's do the math and see where we stand. We'll add the fractions one by one, just as we added the sinc functions to our integral layer by layer. First, integral b1. We use the term with x3. Our sum is just 31. This is about 0.333, which is much less than 1. We are well within budget. The result is 2. Second integral b2. We add the term with x5. Our sum is now 31 plus 5, 1, 155, 4, phi a. This is about 0.5333. Still safely under 1, result 2. Third integral b3, we add x7, sum 315171. This comes out to about 0.676. Still good. Result 2p. Fourth integral b4, add x9, sum 315171. This is roughly 0.787. We're getting closer, but we're not there yet. Result 2. Fifth integral b5, add x11, sum 31517191 1 This gets us to about 0.878. The budget is getting tighter. Result 2. Sixth integral b6, add x113. Our sum is now 31 pulse 5171 91 1 to 1. This gives us approximately 0.955. We are right up against the edge. We have used up over 95% of our budget, but we are still just barely under 1, and so the magic holds. The result is still a perfect 2 pi. Now, for the moment of truth, the eighth integral in the sequence, the one that broke the pattern. This is the one where we introduce the term x15 sen x15. So, we must add its corresponding fraction, 15(1) to our running total. Let's see what happens. 0.955, 151, 0.955, 0. And there it is. For the first time, our sum has crossed the threshold. We have gone over the budget of 1. The moment that sum exceeds 1, the guarantee is void. The secret contract we had with P has been broken. The hidden machinery that kept the result stable is no longer effective. A new phenomenon, a tiny correctional term, is allowed to kick in, and the value of the integral dips just slightly below 2p.
This is the explanation for the what, but it deepens the why. Why is the boundary line at exactly 1? And what does this sum of fractions physically represent? It feels like we've just replaced one mystery with another. We now know the rule of the game, but we don't know why the rule exists in the first place.
The answer lies in the shape of the sinks function and how these shapes talk to each other. The sum of the coefficients, 31 plus 51, is a measure of how stretched the combined functions are. As long as the total stretch is contained, the central humps of all the functions are the dominant feature, and their combined area behaves predictably. But once that sum crosses 1, it means that the functions are collectively stretched so much that the smaller ripples of one function begin to interfere destructively with the central peak of another. The budget of 1 represents the point of first contact. The moment a side ripple is pulled all the way into the central, most important region and starts to subtract a tiny piece of area. The unseen influence of P was there all along, not just as the answer but as the silent arbiter setting the rules of the game. The pattern wasn't a law of nature, it was a temporary peace treaty, and by adding that fateful 51, the Borwein brothers had inadvertently declared the treaty was over. Human beings are pattern-matching machines. It's our superpower. We see 3 stars in a row and call it a belt. We have a few warm days in February and declare an early spring. It's how we navigate the world, and in the finite, everyday world, this intuition serves us pretty well. If you turn a key in your car door and it unlocks 7 times in a row, you have very good reason to believe it will unlock on the 8th try. You don't expect the lock to suddenly change its nature. But the Borwein integral is not a car door. It's not a finite, everyday object. The integral is calculated from negative infinity to positive infinity. It's a question about the total behavior of a function across an infinite expanse. And this is where the rules of common sense can break down. Infinity is a strange and slippery concept, and it loves to play tricks on our perfectly reasonable, pattern-based logic. The story of the Borwein integral is a masterclass in one of these tricks. Let's go back to our budget of 1. As long as the sum of our coefficients 31.51 was less than 1, the integral's value was a stable 2 pi. This wasn't magic. It was a period of grace. During this time, all the important parts of our sinc functions were playing nicely together. Picture the graph of the function we're building. It's dominated by that huge central peak where all the individual sinks functions overlap their main humps. This is where most of the area, most of the value of the integral comes from. Then spreading out on either side, you have the combined ripples. For the first 6 editions, these ripples were just noise on the outskirts. They wiggled up and down, far away from the center, and their net effect on the total area was essentially zero. The positive wiggles and negative wiggles canceled each other out in a complicated but ultimately balanced dance. The core of the function was positive and the fringes were quiet. The budget of 1 is the tipping point. It represents the precise amount of stretching required to pull one of those outlying ripples into the main event. When we added 51 to our sum and it tipped over 1, we fundamentally changed the geometry of our curve. The collective stretching effect became so pronounced that the first valley, the first negative going ripple of the combined function, was dragged inwards. It was no longer on the quiet outskirts. It was now sitting right on top of the edge of the main positive central peak. This is the trick. This is the heart of the bug. For the first time, a significantly negative part of the function was overlapping with a significantly positive part. Imagine you have a big pile of sand, the positive central peak, and next to it, you have a small hole, a negative ripple. As long as they are separate, the volume of the sand pile is unchanged. But the moment you stretch the landscape so much that the hole moves to be inside the pile of sand, it's no longer just a hole, it's a divot. It has removed some of the sand. The total volume of your pile has decreased. This is exactly what happens in the 8th integral. This newly arrived negative ripple multiplies against the positive central peak. And what happens when you multiply a positive value by a negative value? You get a negative value. This process carves out a tiny sliver of area from the main peak. It creates a small dent of negative area where before there was only positive area. The change is minuscule. The ripple is still small compared to the main peak, so the amount of area it subtracts is tiny, so tiny that it only shows up in the 9th or 10th decimal place. This is why the computer's result looked so similar to 2 pi at a glance. It was 2 pi minus the tiny area of that new divot. This is the beautiful subtle trap that infinity sets. In a finite problem, you can usually see all the moving parts at once, but across an infinite domain, a cause and effect can be separated by a vast distance. A ripple that started way out on the fringes, seemingly irrelevant, can be patiently waiting for the conditions to be just right for it to be pulled into the center to do its damage. Our intuition, built on 7 perfect examples, told us the pattern was a law, but the mathematics showed it was just a temporary condition. The trick wasn't a failure of logic, it was a failure of imagination. We failed to imagine that the system was complex enough to harbor such a delayed hidden mechanism. The Borwein integrals teach us a crucial, humbling lesson. When you're dealing with infinity, you can't trust the pattern. You have to understand the machine, and to truly understand the machine, the Borwein brothers had to pull out an even more powerful mathematical tool. Alright, so we know the pattern breaks, and we know it happens when the sum of coefficients, our budget, goes over 1. We've explained it with metaphors about ripples and sand piles, but that's just an intuitive picture. To get the real, rock-solid mathematical reason, we need to use one of the most powerful and beautiful tools in all of mathematics and physics, the Fourier transform.
If that sounds intimidating, don't worry. Think of it like this. The Fourier transform is a mathematical decoder ring. It allows you to look at a problem in a completely different way. Our problem involves a complicated function made by multiplying a bunch of sinks waves together. It's messy. The Fourier transform lets us translate this messy function from its normal home, the time domain, into a whole new world called the frequency domain. And in this new world, the problem becomes shockingly simple.
What does this mean? Imagine you're listening to a piece of music, a chord played by an orchestra. In the time domain, you hear a single complex sound wave hitting your ear over time. It's hard to tell what's going on inside it. The Fourier transform is like having a perfect ear that can instantly break that complex chord down into its individual notes. A C, an E flat, a G, and a high B from the flute. It tells you exactly which frequencies are present and how strong each one is. Our messy Borwein integral function is like that complex chord. The Fourier transform is our way of breaking it down into its simple notes. And here's the magic. The sinc function, which looks like a decaying wave in the time domain, has a Fourier transform that is the simplest shape imaginable, a rectangle. Yes, that elegant, rippling scint wave, when viewed through the Fourier decoder ring, turns into a flat-topped box. This shape is often called a boxcar or rect function. It has a value of 1 over a certain central interval and is exactly 0 everywhere else. The width of this rectangle is directly related to that stretching factor in the scint function. The basic x sincs transforms into a rectangle of a certain width. The function x3 sin x3 transforms into a rectangle that is only 1/3 as wide. The function x5 sin x5 transforms into a rectangle 1/5 as wide, and so on. Now, here's the second piece of magic, a rule called the convolution theorem. It sounds fancy, but the idea is crucial. It says that multiplying two functions together in the messy time domain is the exact same thing as doing a different, simpler operation on their clean shapes in the frequency domain. This simpler operation is called convolution. For our purposes, we can think of convolution as smearing one shape with another. Imagine taking the first rectangle from the first sinc function and sliding the second, thinner rectangle across it, and at each point you measure their overlap. The result of this smearing process is a new shape. So, our original problem, calculating the area under a curve made of 8 multiplied since functions, has been transformed. We've used our decoder ring. The new problem is take a bunch of rectangles of different widths of 1, 1, 3, 1, 5, 1, 5, 1, 7, 2. Smear them all together using convolution. This gives us a final, resulting shape. 3. Find the height of this final shape right at its center point. It turns out that the value of our original integral, that 2 pi number, is directly proportional to the height of this new shape right at its center. So why does the pattern hold and then break? Let's picture our rectangles. We have a main one of width 1. Then we have a bunch of smaller ones with widths 1, 3, 1, 5, 1, 7, and so on. The convolution or smearing process has an interesting property. If the total width of all the smaller rectangles you are smearing onto the main one is less than the width of the main one, the resulting shape will still have a perfectly flat top. Think of it like this. Our main rectangle has a width of 1 centered at 0, so it extends from my 1, 2 to fine 1, 2. The combined smearing width of our other rectangles is the sum we've been looking at, 3. As long as this sum is less than 1, the total smearing effect is contained within the boundaries of our main rectangle. The result of the convolution is a new shape, but its peak is a perfectly flat plateau. The height at the center is the same as the height slightly off-center. This flat top corresponds directly to the integral's value being a constant 2 pi. But what happens when we add the rectangle with width 115? Our sum of widths, 31 plus 51 to 151, creeps just over 1. Now the total smearing effect is wider than our main rectangle. The smearing spills over the edges. What does this do to our resulting shape? The top is no longer a flat plateau, it develops a little dip. A peak right at the center that is slightly lower than the points next to it. The flat top has become a gentle mound. Since the value of the integral is determined by the height of this shape right at the center, and the center is now the bottom of this tiny dip, the value goes down. It's no longer the same constant value, it's slightly less. The Fourier transform removes all the mystery. It translates the problem into a simple geometric puzzle about rectangles. The peculiar pattern of the perfect 7 and its eventual failure is nothing more than the consequence of smearing rectangles together. The pattern breaks at the exact moment. The sum of the widths of the smaller rectangles exceeds the width of the main one, causing the flat top of the resulting shape to buckle. The secret decoder ring revealed that the bug was just simple geometry, hiding in a different dimension. We've now arrived at the final reveal, the moment we can bring the detectives, the clues, and the culprit together in one room. The mystery began with a number on a computer screen, a result that felt so wrong it had to be a glitch. We called it a bug or a mistake, but the truth is the computer was right all along. The ghost in the machine wasn't a software error. It was the ghost of pure mathematics, a hidden structure that was simply following its own rigid, logical rules. Let's assemble the final picture of what happens with that fateful eighth integral, the one that includes the term x15. Conclusion 1. The budget. We established the simple rule of the game. The integral's value stays at a perfect 2 pi as long as the sum of the stretching coefficients, 31 plus 51, stays less than 1. For 6 straight steps, we crept closer and closer to this limit, landing at about 0.955 with the 13. The moment we add 51, our sum becomes approximately 1.21. The budget is officially broken. This is the trigger. Conclusion 2. The ripples. In the world of the functions themselves, the time domain, this trigger has a physical meaning. Breaking the budget is the signal that the functions have been stretched so much that a negative ripple from one of the outer functions has finally been pulled all the way into the core positive region of the combined central peak. A destructive interference, which was previously happening harmlessly on the fringes, is now happening right in the middle of the main event. A tiny bit of positive area is being cancelled out. This is what happens. Conclusion 3. The rectangles. To understand why this happens with such mathematical precision, we used our Fourier transform decoder ring. This moved us into the frequency domain and turned our messy product of sinks waves into a clean convolution of simple rectangles. The rule of the budget translates perfectly. As long as the sum of the widths of the smaller rectangles is less than the width of the main rectangle, which is 1, the result of smearing them all together is a new shape with a perfectly flat top. The height of this flat top gives us our stable 2 pi answer. Now, here is the climax of the breakdown. When we add the 51 term, we are throwing a new rectangle with width 51 into our convolution smearing process. Because the total sum of widths is now greater than 1, the smearing process spills over. The beautiful flat top of our resulting frequency domain shape can no longer be maintained. It buckles. It develops a small, shallow depression right at its center point. The highest point of the shape is no longer at the absolute center. The center is now the bottom of a tiny dip. And since the value of our original Borwein integral is directly tied to the height of this shape at its exact center, the value must go down. This is the ghost in the machine. The computer, when asked to calculate the integral, is essentially performing this process. It follows the rules of calculus, which are deeply and intrinsically linked to the rules of the Fourier transform. The logic is one and the same. The computer doesn't see the rectangles, but its calculations are bound by the same geometric truths. When the convolution shape develops a dip at the center, the numerical integration performed by the computer faithfully reflects this, by producing a slightly smaller number. So the mistake was, in fact, a perfect reflection of a subtle geometric event happening in a hidden mathematical dimension. The pattern didn't just stop. It was forced to stop by the underlying structure of the functions. The first 7 integrals were not a rule, but a happy coincidence of staying within the stable region of this structure. The 8th integral was the first to step outside that region. The Borwein integral mystery is the ultimate mathematical gotcha. It lures you in with one of the most tempting things for a human mind, a simple, beautiful, repeating pattern. It lets you confirm it over and over, building your confidence until you feel certain you've discovered a universal law. Then it pulls the rug out from under you, revealing that the pattern was just the first chapter of a much deeper and more interesting story. The ghost wasn't a poltergeist causing random errors. It was the spirit of mathematical truth, reminding us that intuition is a guide, not a guarantee. So, the case is closed. The mystery of the computer's bug has been solved, not by fixing a line of code, but by uncovering a deep and elegant mathematical truth. We followed the clues from a simple repeating number to the complex interaction of waves, and finally to the clean geometric world of Fourier transforms. But once the dust settles, what are we left with? What does this strange little story about a sequence of integrals actually teach us? The lessons, it turns out, go far beyond the puzzle itself. The danger of obvious patterns. First and foremost, the Borwein integrals are a powerful cautionary tale. They are the ultimate example of the danger of relying on inductive reasoning, seeing a pattern and assuming it will continue forever. For 7 perfect instances, the evidence screamed that the answer would always be 2. It's the most natural conclusion in the world. But in mathematics, a million examples do not constitute a proof. A billion examples do not constitute a proof. Infinity is always lurking in the background, with plenty of room to hide a surprise. This story beautifully illustrates the core of the mathematical mindset, the demand for deductive proof. A mathematician isn't satisfied until they understand the underlying mechanism that forces the result to be true. The Borwein brothers weren't content with the canon, they needed to know why it held. And in finding the why, they also found exactly where and why it would fail. It's a humbling reminder that our intuition is a wonderful guide for exploration, but it can be a terrible guide for certainty. The dawn of the digital detective. This story is also a monument to a new way of doing math. The Borwein brothers were pioneers of experimental mathematics, using the computer as a laboratory for the mind. Before such tools, this pattern may never have been discovered, or the calculations would have been too tedious to pursue. The computer did two things perfectly. It revealed the tantalizing pattern with ease, and then it ruthlessly revealed its breaking point. This case helped cement the computer's role, not just as a high-speed calculator, but as a genuine partner in discovery. It can generate data, test ideas, and present us with mysteries that our human minds are then challenged to solve. The bug was a question posed by the machine to its creators, a question that pushed mathematical understanding forward. It shows the modern relationship between human creativity and computational power at its best. The secret unity of math. Think about the tools we had to pull out of the box. To solve this, we started with an integral, a concept from calculus. The pattern was defined by a sequence of odd numbers, which feels like number theory. The functions themselves, St functions, are the bread and butter of signal processing in physics, and the final, ultimate explanation came from the Fourier transform, a cornerstone of wave analysis. This puzzle is a testament to the stunning hidden unity of mathematics. It shows that these different fields aren't separate subjects in a textbook. They are all different languages describing the same interconnected reality. A geometric property of rectangles in one domain dictates the value of an integral in another. This profound connection between seemingly unrelated ideas is one of the deepest and most beautiful aspects of mathematics. A deeper kind of beauty. Finally, the Borwein integrals teach us something about what it means for a mathematical idea to be beautiful. The initial pattern was beautiful in a simple, orderly, predictable way. It was satisfying like a perfectly rhyming poem. But the full story is beautiful in a much deeper sense. The real beauty isn't in the unwavering pattern. It's in understanding the elegant, intricate machine that produced the pattern and also dictated its collapse. It's the beauty of a complete system, with its rules, its limits, and its surprising consequences. It's the difference between admiring a flower and understanding the delicate dance of genetics, soil, and sunlight that allowed it to grow. The final explanation, with its interlocking parts and its aha moment of clarity, is far more stunning than the simple repetition that first caught our eye. The Borwein integrals are more than a historical curiosity. They are a perfect parable for scientific and mathematical discovery. They remind us to stay curious, to question the obvious, and to remember that sometimes the most exciting journey begins with a result that looks for all the world like a simple bug.